Hi, it's Menaka. This week on The Decibel, we're doing something a little different. For the next few days, it's all about science. Every day this week, we're bringing you some of the biggest science news stories that we could find. From searching for life on other planets, to the hunt for dark matter deep beneath the Earth's surface, to answering the question, did curly hair help our ancestors develop bigger brains? Call it Science Week on The Decibel. Let's get started.
So we're finding tons of different planets that have some really cool and weird features. We found multiple examples of planets that orbit two stars, sort of like, Tatooine planets. Two suns, right? Two sunrises, two sunsets.
Astronomers have been busy cataloging exoplanets, planets outside of our solar system. Some of them are pretty bizarre.
One example of that is WASP 76b. So this is a gas giant. It's what we call a hot Jupiter. It orbits its host star very closely. And in 2020, there was a report that we had maybe seen evidence of iron rain in the atmosphere of this planet.
Yeah, it's so hot on this planet that it might rain iron. One planet seems to be mostly carbon, where the temperature and pressure is so high, the middle might be diamond. And on another planet,
observations they support that potentially the weather on this planet is really, really extreme. We're talking 2 kilometer per second winds. This is about 7,200 kilometers per hour. And a daytime temperature that is nearly 2,000 degrees Fahrenheit. And the possibility of raining down of silicates or glass.
This kind of research is about to see a big boost. Since it launched a year and a half ago, the James Webb Space Telescope has been getting some of the most detailed images and information about the universe that we've ever seen. Canadian scientists are going to be using the telescope to study exoplanets and looking to see if any of them might be able to host life. Dr. Heidi White is an astrophysicist and science communicator with the Trottier Institute for Research on Exoplanets at the University of Montreal. That's one of the groups studying exoplanets using the James Webb Space Telescope. Today, she tells us about some of these planets that researchers have already discovered and how close we are to finding evidence of life beyond Earth. I'm Menaka Raman-Wilms, and this is The Decibel from the Globe and Mail. Dr. White, thank you so much for being here today.
Thank you for inviting me.
What's the purpose of looking for these exoplanets, Heidi? I mean, it's interesting for sure, but why do we do this?
I think in a more practical sense, it's really important to explore other planetary systems because it gives us a lot of insight into the formation of planets, planetary systems in general. Imagine previous to discovering exoplanets, a lot of our insight into how planets form, how solar systems form was based on our own. And we looked at our own solar system and said, okay, we've got the rocky planets, those are the inner planets, we've got the gassy, icy planets in the outer part of our solar system, and that is maybe the standard. And then we started finding exoplanets and discovering different systems. And overwhelmingly, what we saw is that most of them don't look like our own solar system, which kind of highlights the importance of exploring these other systems because they, as a much larger sample, represent, the sort of fundamental processes that go into building planets and planetary systems.
Wow. Yeah, because I guess we just assumed, because this is the only example we have, right, of our own solar system. So we assumed maybe this is the standard, but maybe not then.
Yeah.
Huh. So how many exoplanets do we know of already, Heidi, in total?
So we have almost 10,000 exoplanet candidates that we've identified so far. About 5,500 of them have actually been confirmed. And these planets belong to about 4,000 different planetary systems. So that's a lot of big numbers.
A lot of really big numbers, yeah.
A lot of really big numbers. But on average, this comes down to about one planet per star, at least one planet per star. And that's really interesting because if you think about our own Milky Way, there are hundreds of billions of stars, which means that we could argue that there are hundreds of billions of planets inside our own Milky Way. And our own Milky Way is only one of potentially trillions of galaxies inside the observable universe, which is really, really amazing.
Wow.
And I think you could say that the big takeaway from all of this is that exoplanets are common. Planets around stars are common. And probably the most interesting thing is that the types of planets we most commonly find don't exist inside our own solar system.
So let's talk about some of these new discoveries around exoplanets.
Yeah.
What have scientists found so far using the James Webb Telescope?
So one of the really amazing things about JWST is that it has an instrument on board that is designed to study a lot of different types of objects. But one of the things it's really good at, or will be really good at, is studying the atmospheres of exoplanets. And so one recent kind of very fun discovery was not only the identification of water vapor in the atmosphere of a hot Jupiter, but also gave us the ability to do like a temperature map of its surface, which is really, really interesting. And it's kind of, in a lot of ways, where exoplanet science is going. The ability to look beyond these planets in terms of their mass and their orbital radius into seeing them as fully fleshed out planets like we see in our own solar system, understanding their climates and understanding what's inside their atmospheres. And so this was really, really interesting because we're finding water vapor inside a hot Jupiter. How does that happen?
Could any of the planets that we're looking at here, could they potentially host life?
Certainly. I mean, there are so many opportunities for life out there in the universe, right? So many planets in our own Milky Way, so many galaxies in the universe. I believe life exists out there. But a lot of our insight into what creates a habitable planet and what constitutes a habitable planet, what are the right conditions for life, those are still based on insight from our own solar system. And so when we look to the possibility for life in the Milky Way beyond Earth, we look towards planets that we consider in the habitable zone of their stars. So this is a span of distances around a host star in which liquid water could exist on the surface of a planet. And that's sort of our most basic definition of what it means to be a potentially habitable planet.
This is like the Goldilocks zone.
It's the
not too hot,
Goldilocks
not
zone.
too cold. Yeah.
And we have detected planets. We know of confirmed exoplanets that appear to be in the habitable zones of their host stars. And so those are probably where we would first look for life beyond Earth. One thing we found is that when we study planets around sun-like stars, evidence suggests that up to half of sun-like stars could have planets within their habitable zones.
Wow. That could be a lot. Okay, so when we're talking about the potential for life here, Heidi, what are researchers looking for on planets as signs of life? So yes, we talked about this Goldilocks zone, that they're looking for planets within that zone. But when we're actually looking at an exoplanet, what are researchers looking for to see if there is potentially something going on there?
So we look typically for cases where planets that are terrestrial, sort of another word for that is rocky. They have atmospheres with, volatiles such as like oxygen and carbon, and they're within the habitable zone. And so there's the opportunity for liquid water to exist at the surface. And as we look towards searching for signs of life out there, we look for things like biosignatures, which are features, characteristics, in some cases molecules that can be used as evidence for past or present life. One potential biosignature could be through looking at the color of an exoplanet. We imagine that if there was an exoplanet that had lots of green life, like we see on Earth, right, that might play a role in the color of the exoplanet itself, how it's perceived to us. And so if we found an exoplanet that was really, really green, that might be one example.
But this is interesting because, as you said, all of our knowledge about what life is based off of what we have here on Earth, right? So it is possible then that what is out there could be totally different than our frame of reference and what we know.
Absolutely. And I would suspect that if we could be all-seeing and all-knowing and know all the different types of life out there that existed in our own Milky Way, we'd be really, really surprised by what we find. I think there's a lot of life out there that probably doesn't look anything like what life looks like on Earth.
We'll be right back. Let's talk a little bit now about how the science actually works. How do researchers look for this information on exoplanets?
Most known exoplanets have been discovered using the transit method. And a transit is when a planet passes between a star and the observer. So we're observing some star, and a planet on its orbit passes directly in between us and the star itself. And when it does this, it blocks a little bit of the light that we receive from that star. And so we receive a little dip, a little decrease in the amount of the brightness, the perceived brightness of this star on the sky.
Okay. So that makes sense to me that we can use this method to see if there is an exoplanet there. I guess, how do we know what is on that planet? So if we're talking about, a planet potentially made of diamond or one that rains iron, how do we know that?
So one really awesome thing about the transit method, or I should say systems where we do observe transits, is that when the planet passes in between us and the star, that starlight, if there's an atmosphere, for example, on that planet, it will get filtered by that atmosphere as it passes through on its way to us. And so we can use instruments like spectrographs to deconstruct the light from objects in space and basically show how bright an object is at different wavelengths or different colors. We can observe the light coming from the star when it's not passing through the atmosphere of the planet and look for features. That's sort of our baseline, right? This is a what we call a spectra or distribution of light from that star. And then we can then observe the light after it goes through, as it passes through the atmosphere of the exoplanet, which leaves its own imprint, because the light from that star is interacting with different stuff in the atmosphere that's sort of stamping an imprint on that spectrum when we receive it. And so we can compare, what does it look like when it's just coming from the star against what does it look like after it's passed through the atmosphere. And that tells us something about what that atmosphere, what is inside the atmosphere, what it's composed of.
That's fascinating. Wow. So if we can take maybe the Earth and our sun as an example here and explain it this way. So if someone was using spectroscopy on us from outside of our solar system, what would they see?
The first thing that they would do is they would look at simply the light that was coming just from our sun. And that would set our baseline, right? This is what light from this star looks like. And then what they would do is they would observe the light as it passed through our atmosphere. Now, Earth's atmosphere is comprised of a lot of different things. It has different molecules in it. And as the light from the sun passes through Earth's atmosphere, the components in the atmosphere are going to interact with that light. And that includes absorbing and scattering it. And this is what's going to be that makes that imprint on the spectrum of light coming from our star.
And they would know that looks like a planet is passing this star and potentially then find the composition of the atmosphere of this planet.
Because how that light is interacted with, what interacts with that light is determined by its composition. So they would see what we call like hydrogen features and water vapor features and carbon. Whatever is in our own atmosphere is going to make an imprint on that light.
That's amazing. Huh. Okay, so let's say scientists find a planet that has some of these markers of life. So we all know oxygen, water. How would we actually know, though, if that exoplanet actually does have life on it?
What I can say is that it would not be possible for us to go there and find out. These exoplanets, one thing that's important to remember is that these planets are very, very far away. Even, something like Proxima Centauri. Proxima Centauri b is a planet orbiting Proxima Centauri. And even then, it is literally light years away, which means that even if we were traveling at the speed of light, it would take years to get there. And we can't travel at the speed of light.
Not yet.
Not yet. And so there's really no possibility to go to exoplanets and sort of take firsthand pictures of it and try and assess, visit them and see whether life exists. And so once again, this is where we'd be relying on biosignatures to tell us something about whether or not life exists on that planet.
Have we found any planets that I guess kind of hit all the markers of what we would look for in life? So that would seem very likely candidates for actually having life there.
I guess the short answer is no. We've not found the perfect exoplanet that is, the Earth 2, for example. However, we have found some examples of exoplanets that look, the more we study them, they look like they have similar conditions. So, for example, TRAPPIST-1e, that's a planet that is within the habitable zone. It's sort of terrestrial and is thought to have, potentially water, maybe liquid. We're not sure. But as for right now, I would say TRAPPIST-1e seems pretty interesting.
Fascinating. A lot of what we're finding out now about exoplanets, of course, is because of the James Webb Space Telescope. And I understand that Canadian scientists are really involved in this. So, Heidi, can you just help me understand what kind of role do Canadian researchers have here?
So I would say, Canada made contributions to JWST. There are instruments, technology on board James Webb Space Telescope that were developed and created in Canada. The first example of which is the fine guidance sensor. This is Canadian made. It's an infrared camera. And this is effectively the eyes of the Webb Space Telescope. All of the scientific observations that are happening with the Webb Space Telescope use the fine guidance sensor. The other thing is NIRISS. This is the Near Infrared Imager and Slitless Spectrograph, which is a really long name. But this is the instrument on board that it basically photographs and breaks apart light. It deconstructs it that we get from objects in space to show, as I said, how bright an object is at these different wavelengths. And
that sounds like a really important instrument then when we're looking at these new discoveries.
Absolutely. So NIRISS will be able to study the atmospheres of exoplanets and help us understand better their composition. But beyond even exoplanet science, scientists in Canada and internationally will be using NIRISS to observe distant galaxies. And it could also be used to study objects that are really close together in the sky.
So what kind of research do you think we'll be seeing like in the coming months from Canadian researchers with the telescope?
So this is really, really exciting. Canadian astronomers have been awarded a significant amount of time on the Webb Space Telescope for its next year of observations, about 206 hours.
Which I guess is a lot.
It's a lot.
The scheme of things, okay.
And a little under half of that will be dedicated to exoplanet research. One of the largest programs for JWST in its next year by Canadian scientists will be to do more characterization of the atmospheres of 5 of the best candidates for water worlds.
These are worlds with water, I guess? Or?
Potentially, yeah. Now, what form that water is unclear, right? It could be a thick atmosphere of steam, probably not liquid. And so they'll be looking for signatures of water and other molecules, which will help scientists better understand this strange type of planet that does not exist in our own solar system.
Yeah. Just lastly, before I let you go, how likely do you think it is that we'll ever find evidence of life beyond Earth? I know you said earlier you thought it was out there, but how likely do you think it is that we'll actually find it?
Ever? I'm almost certain we will eventually. Whether that will be in my lifetime, I can't say. But life exists out there. There's simply too many possibilities for life. And so I would say that as long as we keep searching, we'll find it.
Heidi, this was so interesting. Thank you so much for being here today.
Thank you.
That's it for today. I'm Menaka Raman-Wells. Our summer producer is Nagin Nia. Our producers are Madeline White, Cheryl Sutherland, and Rachel Levy-McLaughlin. David Crosby edits the show. Adrian Chung is our senior producer, and Angela Pacenza is our executive editor. Thanks so much for listening, and I'll talk to you tomorrow.